будем начинать. Я буду говорить на английском, потому что мне удобнее. Практически все технические презентации я делал на английском последние десяток лет. Hello everyone, thanks for attending this talk. And my name is Artem Chebotko, and I'm from DataStax, solution architect at DataStax, the company that is behind Apache Cassandra, developing Apache Cassandra, integrating it with a number of other technologies, including Spark. So we're going to talk today about big data-driven applications with Cassandra and Spark. And the agenda. So here is the agenda of this presentation. We're going to discuss in general modern big data and cloud applications. So we had a number of presentations before, but we never talk about requirements for those applications actually. And we will talk about the roles of Spark and Cassandra in fulfilling those requirements. Then I'm going to introduce you to Cassandra and Spark, give you a short overview, and we will talk more about architecture and languages and APIs that are used there. And I will primarily focus on writing code for accessing Cassandra from Spark. So essentially Spark Cassandra connector. And hopefully we'll have time for a brief demo. So the requirement of modern applications that we develop in now, especially applications that work in the cloud and work with big data, include the numerous endpoint, which means you probably will consume a lot of data that will come in different formats, okay? And you will have to integrate that data. You will also have different types of application working with the same data. You will have your application working with users who are in different locations. You need your application to be always available, right? If it's there should be zero downtime, otherwise you're going to lose money. And your application has to be fast, whether it's real-time application, OLTP kind of application, or whether it's decision-making, more analytical type of application. And you also want it to scale. You have 1,000 users today, you may have 50,000 users tomorrow, right? You don't want to have an issue of not being able to serve their requests. In terms of response time and workload, the applications are divided usually in operational and analytical. And we had a number of presentations on those today in this track. So examples of OLTP or operational applications would be real-time applications that are working with web, with Internet of Things, just collecting sensor data type of application, financial transactions, and so on. Okay, there are some applications that would be kind of in the middle, like real-time analytics, like recommendations. Like to compute recommendations, it may take a long time, but you need to deliver recommendations to user pretty quickly. And streaming applications, we had a number of talks about those. Example, fraud prevention, right? You need to analyze the data as soon as it comes and prevent, for example, fraud financial transaction. Okay, and there are also batch analytics. So these are slow applications and they are not facing user. And those include batch analytics, include the predictive models, for example, to predict a recommendation for a user, and something like a fraud detection when you analyze a large data set and decide that there was a fraud committed at some point back in the history. Okay, so Spark and Cassandra together, so none of them is going to solve all of these problems, but together they complement each other. They can fulfill all the requirements that I mentioned, and they can also, Cassandra is going to work on OLTP side, it's a database, and Spark is going to be a framework that can handle analytical side. Okay, so I'm going to briefly introduce you to these technologies, but especially you had a lot of talks on Spark today. So Cassandra is operational database. It's distributed database. It is capable to handle millions of transactions per second and can do it very quickly. Of course, depending on your cluster size, right? But there are deployments that deal with that scale, with petabytes of data, with thousands of nodes in a cluster. Okay, system, the database system has linear scalability, meaning that if you have, if you need to improve throughput of your cluster, you can double your cluster or triple your cluster, and you're going to double or triple your throughput. Okay, and another great feature that helps to fulfill one of the requirements is that Cassandra is always on. It's continuously available. Okay, so it's very hard to destroy the cluster, and especially if you set up multiple data centers. Even we had situation when hurricane would take down one data center in New York, and you still have a data center in Los Angeles picking up all the requests, and there is literally less than a second delay for for users who are using the application. Okay, there are a number of companies that use Cassandra in production. Okay, so here there is just probably 1% of them represented here. There are literally over 1,000 of different companies, and the main use cases would be personalization, like Customer 360, product catalog or inventory management, also fraud detection. A lot of financial organizations use Cassandra. Financial transactions, the IoT, the Internet of Things, time series type of data, recommendations, and of course messaging. Okay, again, this is just a small number of those companies. Now Spark has a different goal. It's a distributed analytical or analytics platform. It supports near real-time analytics, also streaming analytics, batch analytics. And as we already heard today, it can be up to 100 times faster than Hadoop, primarily because it handles a lot of operations in memory. It has good scalability and fault tolerance, being able to recompute lost data as long as the original data source is available. Okay, and it has very rich, versatile API. There are a number of companies that use Spark. Pretty much most of the companies that in big data, they somehow use Spark for some of the projects. Okay, and the Spark has a number of supports number of languages, including Scala is probably the #1 language, and also Java, Python, and R. There are, besides the core Spark, there are a number of packages that are available, like SQL and streaming, machine learning, and graph processing. Okay, so my talk is going to focus mostly, after we're done with introduction, background part, I'm going to mostly focus on the Spark Cassandra connector. Okay, so Spark Cassandra connector is another open source package. It's developed by DataStax, but it's open source. And it allows you to read data from Cassandra and to write data back to Cassandra. But also there are a number of optimizations that you have to consider if you want your code to be efficient. So I'm going to show you some tricks, some magic, how you can write more efficient code. Okay, so let's look a little bit at the architecture. So Cassandra has distributed shared nothing peer-to-peer architecture. Okay, there is no master, there is no primary node or cluster manager or things like that. So you always have all nodes that are peers, okay? Which means that you can lose the node and other nodes can handle the same task because they all pairs, as long as you have your data replicated. Okay, and also it means that you can connect to any node in your cluster, so there is no special node to connect to. All nodes are the same. Okay, in terms of partitioning and replication in Cassandra. So you always want to replicate your data when you store it. The data is stored in tables, and every time you're going to store data, the unit of distribution will be a partition, right? So a partition will be stored on some node, and this is decided based on partition key. Okay, and so essentially here I'm showing you the write request. You have a client that wants to write this partition into your cluster. You have a cluster with 6 nodes there. You connect to any node in the cluster, and that node takes the role of coordinator, and it has partitioner. Based on partition key that you specify, it decides which node is going to store, or which set of nodes is going to store that particular partition. Okay, and it decides that it finds 3 replicas in this case, because we're using the replication factor of 3. So we're going to store our partition on 3 nodes. Okay, then there is another important concept in Cassandra called consistency level. And in this example, it's set to quorum. What it means is that we're sending our data to store on 3 nodes, but we are waiting for response. The coordinator waits for response from majority of the nodes, from the quorum of the nodes. In this case, 2, right? The first 2 nodes will respond that acknowledge that data is written, and based on that, coordinator will acknowledge that the data, the request is successful to the client. Okay. Another example how you read data from Cassandra, and that will be important to understand when we when we use Spark to do that. Okay. When you read data from Cassandra, you still specify the partition key when you read one partition. And again, you have consistency level for each request. In this example, it's 1. So meaning we need to get the data from only 1 replica. Even so we have 3, the coordinator is going to contact only 1 replica to get the data and will return it back to the client. Of course, it's customizable, it's tunable consistency. If you want to read with quorum or you want to read with some other consistency level, it's all easy to do. Now, Spark has a different architecture. It's not, unfortunately, it's not peer-to-peer, so it's a master worker architecture. So you can think about master being a single point of failure, and to solve this problem, right, to make it fault tolerant, you will have to set up failover masters, reserve masters, and so on. In some systems like DataStax Enterprise, the nodes can even automatically elect a new master if there is a problem. Master is usually lightweight, and the Spark client contacts master just to allocate the resources. Then master talks to workers to allocate those resources in terms of executors here, and the executors will work directly with the driver with Spark context, which will schedule the jobs and tasks on those executors. So the driver is another, you can say it can be a single point of failure, because the driver is responsible for getting all the computation and organizing it. It's scheduling it essentially. So it will the computation will be represented internally as directed acyclic graph, and it will be divided into jobs, and then jobs will be divided into stages. The stages are usually delimited by a shuffling process that we're going to talk about a little bit later, and each stage has tasks, and those tasks are essentially identical, right? And the task is scheduled by the driver, by Spark context, is scheduled on tasks are scheduled on executors here, and the cache for executors holds Spark partitions, so chunks of the data that each task is going to process. Okay. So for these two technologies to work together, you need something to connect them, and this is called Spark Cassandra connector. So it's essentially a library or package that allows Spark to talk to Cassandra. Okay, so deployment will look like this. More precisely, We have 3 nodes here, 3 physical cluster nodes. On each cluster node, we have Spark deployment and Spark node deployment and Cassandra node deployment. So you can see different JVMs. One of them will be master JVM, which is usually lightweight. There is worker JVM, but the most important will be the executor JVMs. They are going to do the real computation that can be expensive. Okay, and there is Cassandra JVM as well. So this is how. So in this example, we have 3 nodes. Total physical nodes. It's always a good idea, it's always a recommendation that you use this kind of deployment, because this allows data locality that I'm going to talk about a little bit later. When you read data from Cassandra, it stays in Spark on the same node, doesn't have to go through the network, transferred to a different node. Okay. And then, now the question you may have, if we combine those 2 technologies together, then we now suddenly have a Spark that is computationally expensive usually, can be very long-running tasks, and you have Cassandra, which has to serve real-time transactions. It has to be very fast, right? Millisecond time response. Then you have to separate workloads by creating multiple data centers. So essentially you're going to have 2 data centers that can be either physical data centers or logical data centers. One will have nodes that only run Cassandra, and they serve very fast real-time transactions. So it's an operational data center. And the other data center would be Spark plus Cassandra. It's analytics data center. So in other words, if you're going to run complex computation that takes a lot of resources in analytics data center, you will never affect performance in the operational data center, and vice versa. Okay, so this is how you're going to do it. And similarly, if you it's pretty much similar scenario when you implement the search, and we talked about, we had presentation on earlier today, like if you're going to use Solr with Cassandra, if you create Solr indices with Cassandra, then you're going to have a separate data center that can handle search. That will be still more expensive than just Cassandra transactions. Okay, so the main part here, if you're going to, if you're only starting with Cassandra and Spark, and these are some of the things that you need to learn first. The first thing will be data model and Cassandra query language, and the other one for Spark will be the core API and Spark Cassandra connector API. Okay, and I'm going to briefly talk about a few, actually 3 tables that I'm going to have in Cassandra that we're going to use Spark with. We're going to read the data from those tables later. But the way you define schema in Cassandra, you start with key space. Okay, key space serves the role of a database or database schema, and in addition, it has, you specify all replication parameters in your key space. This is how easy you can set up replication. Here you have 2 data centers, one in Kyiv, which could be operations data center, another one in Houston, and you have different replication factors, 3 and 2. So your data will automatically, you don't need to do anything, will replicate between those data centers. Okay. And then the first table, the CQL, if you never used it before, then it will look very much like SQL, and that is done on purpose. But there are differences that I'm going to highlight. So first, this table, it's a table with single row partitions. So we said that Cassandra stores data in tables, and tables divided into partitions, partitions distributed, but then partitions contain rows. Okay, so in this example, it's a simple table with users, and we have username as a partition key, and essentially we have 2 partitions, one for Alice, one for Alex. They can be stored on different nodes in your cluster, and each partition contains only 1 node. So by looking at the CQL, the create table statement looks just like SQL. There is, however, one big difference. When you try to query this table, the only query you can do is to query based on username. You can retrieve the whole row or the whole partition in this example. Okay. Of course, you can set up some additional indexes, either Cassandra indexes or Solr indexes, to query based on other, or maybe materialized views. Okay, another example, which is still a table with single row partitions, but it no longer looks like relational table because it has settings, which is the map, right? It's not atomic column there. So this table stores information about sensors, their IDs, type, settings. So we have users table, we have sensors table. They look pretty much similar, and they are queried similar. But now I'm going to show you the table with multi-row partition. So I'm going to take the sensors and will nest them under user partitions, essentially. So I have two partitions in this example. Each one belongs to a different user, and each partition has multiple rows. So sensors that user owns. Okay, that user owns. So I have 3 rows in the first partition, and by default the rows are sorted based on ID. ID in this case now called clustering key. So username is still partition key, but then ID is a clustering key. So I have this table, and most of your table in Cassandra will be multi-row partitions where you're going to use partition key and clustering key in your table definition. So how do you define clustering key? It's very simple. The difference is the first component is always treated in the primary key definition is always treated as partition key, the second as a clustering key. Okay. Now once you introduce clustering key, you have more options for querying and even sorting, ordering. Okay, so you can query based on partition key still, or based on partition key plus clustering key, range search on clustering column, and ordering on clustering column as well. Okay, so I'm going to use these 3 tables in the next few examples where we are going to read the data from these tables into Spark. Okay, so this is the first simplest example, and we're reading from table sensors by user and selecting 3 different columns. So what happens? This API here. So the first, this object SC, it's a Spark context object, right? So I didn't define it, but it's pretty easy to define. You just specify the master node you connect, some configuration, and you can create it. Okay, but then the API here is Spark Cassandra Connector API. It's not really Spark API here. So I'm reading from this table and I'm selecting these 3 columns. Internally, it's going to result in this SQL query where we're selecting the 3 columns from this table. Okay, from this table in a given key space. Okay, now I'm going to change this example a little bit. I'm going to use this filter. Okay, I only want to keep the rows where username equals Alice. Okay, looks good, right? The filter is a transformation in Spark. So after you select data, Spark Cassandra selects data with SQL, you execute filter with Spark. However, this is not the most efficient approach you can use to do that. Instead, you can, the reason it's not most efficient is because this query is going to retrieve all the data from your table, and then you're going to give it to Spark, and then Spark is going to filter that. Okay. Instead, what you can do, okay, you can, instead of filter, you can use where, which is Spark Cassandra Connector, and you specify that condition username equals Alice, and you get this SQL query, so Spark doesn't have to be involved at all, and you only retrieve 1 partition. This is possible because the username is partition key in this table, right? It's not going to work for any predicate, but in this case we can push down predicate because username is also a partition key. Okay. Another optimization that is used is data locality, and this optimization comes for free essentially as long as you deploy Spark and Cassandra together. When you read data from Cassandra into Spark, the data will stay on that node, it will not be moved to a different node, and so on. So there is data locality. And the way it's done is there are certain settings. By default, you read consistency with consistency level local 1. Of course, you can change that. The local one, we saw the consistency level 1 in the previously in the examples. Local 1 means it's local to a specific data center that you are connecting to. And then Spark partition will be 64 megabytes by default. So if you have Cassandra partitions that are smaller, then you're going to have multiple Cassandra partitions stored in or represented as a Spark partition. And there are other settings that can be useful to optimize reading. So another optimization will be join, right? Cassandra does not support joins at all, because joins, no matter what you do, joins will always be very expensive. Okay, joins will always be very expensive, and this is example of a standard join that you can use in Spark. Okay, it's not Cassandra specific or anything. The only Cassandra specific is you read in data from Cassandra table here, table sensors, and you're going to create a key value pair RDD out of just Cassandra RDD by using key by transformation. So you're going to organize, you're going to have your rows organized by owner. Okay, and then you read in data from the second table, users, that you saw before, and you organize in data by username. After that, you can simply call join, and you're going to join these two tables. So you will essentially find which sensors belong to which user. So this is standard Spark join, and it's expensive because you have to shuffle two data sets. Okay, how many of you know what shuffling is? Okay, so I'm going to talk a little bit about shuffling to give you an idea. So the shuffling is essentially repartitioning your data. So you get your Spark partitions, data in Spark partitions, and you are going to reorganize your data to create new partitions with a different property or different condition. And the way it's done is essentially you're going to take the original partitions 1, 2, 3. You're going to have a task for each one, and each one is going to map the data into buckets, which will go to disk, okay, which will be stored on disk. So you have I/O in Spark. Yes, you have I/O in Spark. It's not only in memory. Then the task, the reduced task, that we're going to pull the specific buckets. For example, a bucket is going to go to the first task here from all the nodes. So you're going to have a lot of traffic, right, in your network. You're going to have external sorting, you will have compression, decompression, things like that, right? So it's very expensive, and you're going to do it twice for two data sets. So how can you do better? You can apply join with Cassandra table transformation that is part of the Spark Cassandra connector API, and you can essentially, in this example, it's basically a natural join with specifying condition. Join the RDD that you read from Cassandra, and select those columns, and we rename in column owner to as username, so we can do the natural join, just like in the relational database. And then we're using this join with Cassandra table, and we specify in second table and condition of this join. Shuffles are eliminated, but there is no data locality. And the reason why there is no data locality, I'm going to show you here on this illustration. So this is the RDD where you renamed owner to username. Okay, and for each owner, for each Alice record or Alex record, you're going to, this transformation is going to query our Cassandra table. So you're going to execute multiple queries for Alice and multiple queries for Alex to retrieve data, then do Cartesian product in memory and return the result. Okay, so there is no data locality. The Alice row here or partition can be on the node, on a different node where this element, this record in RDD is located. There is no data locality. So it's almost like a one shuffle. Okay, so the last trick with a join is I can get one shuffle, but I can keep my data locality. And that is done with this transformation, Repartition by Cassandra Replica. What this transformation does, it takes the RDD, existing RDD, in this case, it's RDD that we create by reading data from sensors, and it repartitions elements in that RDD the same way as data is partitioned in Cassandra in table users. Okay, in this transformation, the last parameter, right? The table user. So it repartitions the RDD based on Cassandra partitioner. Okay, and internally it looks like this. Okay, so we are going to take this RDD and repartition it so that all Alice records, we repartition based on the username, all Alice records will be on the same node where we have the Cassandra partition. So your join is going to have the data locality between these two and these two partitions. Okay, but still repartitioning is what shuffle is. You still have shuffle. So join is never, if you can avoid join, you should, because it's expensive operation in any case. But you can at least do at least twice better than by default with standard join. And the last optimization here, for shuffle-free grouping, you can sometimes completely avoid shuffling when you group in data. So in this example, I'm reading from table sensors by user, and I'm reading 3 columns, and I'm transforming my Cassandra row that I get, each Cassandra row, to a tuple key-value pair where username will be key and ID and type will be value. And after that, I'm grouping by key. So what happens here, you have part of this executed by Cassandra as SQL query, and another part will be executed by Spark as group by key. And group by key, guess what it's going to do? It's going to shuffle, right? Most of the key operations, they're going to do shuffling unless there is a specific partitioner on the data set that suits their goal. Okay, so there is a shuffling here. So this is the best optimization you can have. You simply, instead of group by key, you can use span by key, which is not Spark API. It's again Spark Cassandra connector API. And the reason you can use it is because, remember this table sensors by users? We already have data partitioned in Cassandra based on username. So there is no, so if you replace group by key with span by key, Cassandra can do all of that for you. It's simply the Spark Cassandra connector is going to set appropriate partitioner on your resulting RDD, and there will never be need for shuffling. So you can see even our query didn't change, SQL query. We just simply eliminated the shuffling here and that Spark work. Okay. Okay, and then if you need to save your data, once you retrieve it, process it in Spark, you need to save it back to Cassandra. There is an easy way to do it. Save to Cassandra. You specify a key space, table, and also columns, and you can easily do it. There are a number of settings. By default, you're going to use local quorum, and again, depending on your needs, you may change it. If you're going to use local one, it's going to be more efficient. Okay, or maybe you're going to, you can still write in 2 nodes or 3 nodes instead of majority, depending how many replicas you have. Okay, and then there are some parameters for how you're going to, how Spark Cassandra connector is going to create batches. The data inserts are organized in batches first, and then the data batches are going to be written. And by default, the inserts are going to end up in the same batch if they have the same partition key. There is a size of a batch, default size, and the number of batches you can have, the task can have concurrently. And also for each Spark task, how many threads you're going to, how many batches you're going to write concurrently as well. So these are default settings, but you should understand that my Cassandra partition and your Cassandra partition, your data will be totally different. My partition may contain 1 megabyte of data, and you may have only 100 kilobytes, right? So that, based on that, you may change these settings and will be able to achieve faster performance. Okay. So I'm going to show you a small demo where I'm going to show you an example of recommendation system that uses Spark and Cassandra. Okay, and I'm going to, for this purpose, I'm going to, so I don't have to switch between Spark shell and SQL shell, I'm going to use Jupyter Notebook. Okay. So this is a music recommendation system, and this is the resolution is not so good. So the idea for this recommendation system, and again, I just extracted some code to give you an example of how we're using Cassandra and Spark together. Okay, so the idea is we have a number of musical albums, and the album is, for example, identified by title and year, and users leave ratings. They rate those albums. So here there is a table ratings which contains some information, user ratings. So each user either likes or doesn't like or neutral to an album, and this is stored in Cassandra. We collect the data very fast, and then we have the offline module which is going to do predictive modeling based on collaborative filtering. Essentially, it's going to be, I'm going to show you, it's implemented in Spark, and it's going to compute the final recommendation. So this module can run overnight or can run for many hours, but then it's going to compute the results, and we are going to store recommendations into this table. So for each user, we are going to be able to recommend some albums to listen to. And then there is a recommender, which is online type of application. The user is not going to wait for hours to get a recommendation. The recommender is going to read data from this table and going to provide recommendations to the user. So what I'm going to, so some CQL that I've been talking about, I'm going to drop this key space, and I'm going to create a new key space for music. This application is running in VM, so it's on this particular computer. I have only one node in my cluster. I'm going to create a ratings table, and I'm going to populate it with really small data set here. I don't know, is it visible? It's big enough? Yes. So really small data set, CSV file, and with 5,000 rows. The reason why it's so small, because I told you that predictive modeling can run a long time, and we should be able to retrieve a few rows and see how they look like. So the user is identified by UUID, and there is a title, and there is a year and rating for the album. We're also going to create table recommendations, right? The one you saw in the illustration, and we're going to select from that table, and you can see it's empty. There is nothing in that table. We need to use our predictive component module to populate the table. So predictive modeling, I'm not going to be able to explain it in detail because it's going to take the next 30 minutes, even so the code is not large. But the idea is quite simple. Based on collaborative filtering, we extract some features from users. In this case, these are ratings. And then based on those ratings, we find users with similar tastes. Okay, so it's like similar items problem. And the way we can find the users that are similar, we measure some kind of distance between them. For example, cosine distance. Essentially, if you represent each user rating as a vector in space, multidimensional space, and then you're going to measure the angle between two different vectors, then you can decide if the angle is really small, then you can decide that these two users are similar. They have similar tastes. If it's different, then you are going to say that they are not similar. Okay, I'm going to skip it looks maybe complex, but it's really not, right? There is just summation there to compute the similarity, cosine similarity, multiplication, and the square roots type of thing. So this is extracted code in Scala that is going to compute those recommendations. So I'm defining some of the functions. I'm going to run the second part, and it's going to take a little bit longer, maybe 1 or 2 minutes. And they essentially, we are doing computation here, but the most important part, or the part that I can really show you in this demo, is at the end we are saving recommendations back to that table recommendations. Okay, back to that table. So we computed them, we saved them, and it's still running, and it just completed. Good. So I can open the last part, which will be very, very simple. Let me stop this. So the very last part, the online analytics, it has to be very fast, so it has to be very simple. And you can do it with Spark. You simply read data from that table that we computed recommendations for. So you use either Spark for that, or you use Cassandra for that. And before we had empty table, now it's going to have some data in it. So in this case, we're going to randomly retrieve 3. Okay, it was warming up, and going to be faster next time. Okay, so you get some data retrieve, some recommendations for a particular user ID. Okay. Okay, and this is essentially all I wanted to present to you today. If you have any questions, you can contact me, but also I want to give you a great resource where you can learn about Cassandra and Spark more. Free online video courses with exercises at academy.datastacks.com. Okay, so thank you, and let me take some questions if there is still time.
Okay, thank you for your talk. I have 2 questions and 1 correction for you. It would be better if you look on it. So you said that Cassandra don't have a single point of failure, yeah? It's correct, but Cassandra has seed nodes. And if we have only 1 seed node in cluster, so it is single point of failure, because seed nodes use by other nodes to learn cluster topology. So if this node will fail and there won't another seed nodes, it's a single point of failure.
Well, that's true, but it's the same type of problem that if you say, okay, I'm not going to even replicate the data, replication factor will be 1. Then if you're going to lose a node, it had some data, it was never replicated, of course you lose your data. Similar, yeah. you need to set a few seed nodes. It's not just 1. Because
it was just a recommendation.
Yeah,
and the question was, you said that it is correct to deploy Cassandra and Spark Spark workers on the same machine, yeah?
Yes.
But if I understand correctly this flow, we use any one node of Cassandra cluster to connect. And when we run a Spark job, then all of our workers will go into that node via network and ask what they have to do. And this, is there any guarantees that this node will redirect Spark jobs into the same machine where is located Cassandra nodes on the. You understand, I hope.
Not exactly. I'm not sure. So the question is, what happens if?
Yeah, you said that it's correctly to keep Cassandra on the same machine with workers,
Yes.
yeah, to avoid data transfer via network. But anyway, these workers will go into network to some node, which is configured in Spark Cassandra connector. Yeah, and is there any guarantee that they will back to the same machine to avoid network transferring?
No, the Spark Cassandra connector is going to. It's just a library that
Okay.
it's a jar file that each Spark node, each Spark deployment will have access to that jar file. So you're going to only that Spark node is going to read data only from the Cassandra node that is on the same physical node in the cluster.
But then each worker should know IP address of the same machine, where it's located. Because if you configure our pipeline to connect into only one node in cluster, so how other workers will know IP address of... Okay, we can keep this talk maybe.
Yeah, it's actually not workers, but the executors. They are going to talk
right.
to the driver. But
okay, let's continue.
Yeah, they don't have to connect to other nodes. Yeah.
Thank you. One question: is this approach unique for Cassandra plus Spark? Or could it be also ported to, for example, Mongo plus Spark and other distributed NoSQL databases? Or it has something unique with Cassandra?
No, you can essentially. It's also what Taras talked about. This is like a Lambda architecture here, right? You store your data in Cassandra. You can also aggregate, for example, compute aggregates using Spark and store it back into Cassandra. But you can use different storage, of course. You can, instead of Spark, you can use Hadoop, right? Instead of Cassandra, you can use something else. But depending on the choice of the technology, you will either meet certain requirements, application requirements, or not.
Thank you.
Like which other connectors?
Like, for instance, if you use Mongo, is there any like alternative? Is there like Mongo connector for Spark or kind of stuff like? Because those features that you showed, they are like related to Spark and Cassandra only, because a lot of people like invest own time into do that. Like.
Yeah, that's right. So the different connectors will have different features, and it's not necessarily you're going to get the same type of join optimization if you're going to use different connector, different database. Okay, because different databases store data differently, essentially, different data models. Out of time. Okay, if you have any questions, we can talk after the